Hey guys, this is Mr. Marchman. I'm here with your second lecture on definite integrals. Today we're going to talk about uh, estimating a definite integral using trapezoids. And so go ahead and turn to lesson 5 in your note sheets, and we will get started. If you remember correctly, we spent last lecture talking a lot about finding the definite integral and exploring how the area underneath a curve can be found sort of by counting the number of squares that were in the curve. And so you needed this like graph paper in order to do that, in order to sort of visualize that. What we're going to do today is we're going to look at a more efficient way of doing that, and that's dividing that area underneath the curve into trapezoids. And so, we're probably still going to have some spots that maybe we miss a little bit, but it'll give us a pretty good estimate as to the area under the curve by looking at that. So let's take a look. Let's look at the first example. Here we have a band, Rascal Mats. They have a new song being downloaded at a rate of 8,000 times per week. And so you can see this represents the rate at which their song is being downloaded. And so for a little while, the rate begins to increase, and then the rate begins to decrease. Again, this represents the rate, not the number of downloads, but the actual rate at which those downloads is being, that song is being downloaded. So what does this integral represent? So from 0 to 8, what does this integral represent? I want you to think about that. From 0 to 8 weeks. What does the area underneath this thing actually tell us? What it does is it tells us the total number of downloads over those first 8 weeks. Okay, the total number of downloads of that song over 8 weeks, over those particular 8 weeks. And so, for instance, if I had done the integral from 0 to 4, it would tell me the total number of downloads of the song over the first 4 weeks. If I did the integral from 2 to 5, it would be the total number of downloads from week 2 to week 5. And so the area in this case is going to tell me the total number of downloads over that span. Now, if I wanted to find do this the old way, I could count the number of rectangles, or estimate the number of rectangles in each under this curve, and I could find a pretty good estimate for the number of downloads. So let's see how I do that. Okay, ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 blah. All right, keep going, keep going, keep going. Looks like there's 1, 2, 3, 4, 5, 6, 7, 8. So there's 32, pretty close to 40. Let's just say, I'm going to estimate that's about 49.5, let's say, rectangles underneath that curve there. And so, well, let's look real quick. How many downloads is that? Well, each rectangle is 2,000 downloads per week tall and 1 week wide. So each one represents 2,000 downloads. I'll call it DL, downloads. I don't like the way I read that because it makes it look a rate. Downloads. So 49.5 times 2,000 gives me, somebody do the math for me, that gives me 99,000 downloads. 99,000 downloads in those first 8 weeks. That's an estimate by counting the number of rectangles. Now, I went really fast because I had already counted the rectangles, but it would take a long time to sit there and count all those rectangles, wouldn't it? So instead, let's do this a different way. Let's divide this region into 4 trapezoids. So of equal width. The key here is I want to always do this with equal width, and I'll show you, sort of tell you why we do that in a second. So equal width means if I'm going from 0 to 8, I'm going to do these with a width of 2. You can sort of imagine like that, right? So Here's one trapezoid. See that I'm kind of connected at the top like that. And here's the second trapezoid. Try to draw a straight line here. Here's the third trapezoid. And here's the fourth trapezoid. So we can call this, I'll do this solid line here. Ugly, but that works. So let's call this like A1, A2, A3, A4. And so you can see I have 4 trapezoids that are going to, if I found the area of those 4 trapezoids, that would give me a pretty good estimate as well of the area underneath that curve. So what I want to do is I want to estimate the definite integral by estimating the areas of the 4 trapezoids. Let's take a look. So here we go. If you remember correctly, what is the area of a trapezoid? Okay, the area of a trapezoid is 1/2 the base times the sum of the heights. 1/2 the base times the sum of the heights, where we have a base of 2 every time, and we have heights that are changing based on the actual rate, right? So let's look at an estimation here. Let's find the area of the first thing. So the area of the first trapezoid has a height of, well, let's see, 1/2, so 0.5 times 2 times the sum of the heights. Well, the first height is, let's say, 8,000. Oops, the sum of the heights. First height is 8,000. The second height is right around 14,000. Okay, and that gives me 22,000. The second trapezoid, 1/2 the base times the height. Well, look, it had the same height, same original height, right? Oops, plus. Then the second height was that. That gives me 27,600. The third trapezoid is, hey, look, 1/2 the base times the sum of the heights. Interesting that it's going to start off again with that original 13,600 plus, and that gives me 25,600. And then the fourth trapezoid, plus 10,700 gives me 22,700. Okay, so if I add up all of these, right, add them all up, that gives me a total of 97,900, which it's asking me now, is that an underestimation or an overestimation? Well, let's look at the picture here. These trapezoids are all underneath my curve. In fact, look at this gap here. There's 2 big gaps that I can see definitely here. Does that mean I'm going to have an overestimation or underestimation? Well, that means that the number that I have, the area that I found, is going to be much less, not much less, but hopefully a little bit less than the actual area. So this is an underestimation. An underestimation of the actual area, the actual integral from 0 to 8 weeks. Okay, so then rather than estimating, here are the values of R of t at each one of those. So now we have actual values. They're actually giving us the number, the actual rate at each one of these times. And so I can actually find, all right, the integral, or a better estimation for the integral, using each one of these. Now, how many trapezoids am I going to use here? Well, now that I have all these different numbers, I can use more and more trapezoids. And you can imagine, as the number of trapezoids that I use increases, the better estimation I'm going to have of the area underneath there. So let's take a look. And here's a little trick here. If I want to find the total area, I'll use A. The total area is going to be 1/2 the base, which if I have the same base every time, let's say it's 1, that's going to be easy. 1/2 the base times. Did you see up here how my first trapezoid had a first height and had a second height? My second trapezoid had the same second height that my first one did. Do you see that? So that the height here was the same between those two trapezoids. And then the same thing occurred here, 13,600. The next trapezoid had an initial height of 13,600. And the same thing happened. So the same thing will go on and on and on. That each two trapezoids will share sort of one of their heights with the next. And so if I think about that, the initial height is going to be unique. So I'll call that H1. But the second height, I'm really going to be adding. There's 2 of those. And the third height, blah, 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 until I get to sort of the 7th height. And then the last height will be unique as well. So sort of like how this 10,700 was unique. So I have this sort of this new formula that I can use to calculate the sum of all of these trapezoids. Because they share the same base, I can do it this way. Now remember that your base is 1. Okay? So I end up with 1/2 8,000 plus 2 times, right? Plus 2 times 13,684. And you guys can sort of do this along with me as I go through. Hopefully I don't make any stupid mistakes here. Oh, got the last one. The last one, remember, is unique. So I need to make sure I have that simply written like that. Okay. And then with a flick of my wrist, magic wand, I can sum all these up, divide by 2, and that gives me a total area of 98,931.5. And what are my units? What are my units going to be here? Oh yes, downloads. So someone was stuck halfway through a download. Interesting. Is this a better estimate or a worse estimate than example 4? It was a better estimate. Why? Because there were more trapezoids, right? Better estimate, more trapezoids, less gap going to be here between my trapezoids and my curve. All right, so there's our trapezoid rule. A little bit of a painstaking process, but also a very valuable way to find area underneath the curve or estimate area underneath the curve. So here's Izzy Fast. Izzy Fast is running a marathon, and they are speeding up and slowing down based on the time. Starts off going 5 miles per hour and speeds up and slows down based on how he feels. I want to sketch the graph that they've given me here. And I want to, so drawing it from 0 to 4 seconds-ish. If I look at my graph, it might be a little bit more difficult to draw this. And so what I'm going to do is I'm going to go to Desmos here real quick. I'm going to draw this. I'll go ahead and get rid of these. I'm going to draw this graph here. F of x equals, I never have to use x and not t's here. So x plus 5 plus sine of 2.9x. Oh, and then I have a funky graph. I have a very interesting looking graph. And so I need to make my window look like this window. So notice this goes from 0 to 9, from 0 to 4. So I want to make my x-axis go from, I'll make it from -1 to 5. So that way I can see a little bit more of that. And this one I'll have from -1 to 10. And there we go. Now you have a pretty good picture of what we're looking at here. There's what it should look like. Okay. And so my graph, I'm going to make it zoom out a little bit. I'll go to 12. There we go. That way you can see the whole thing. So my graph is sort of this up and down increasing periodic function here. And so what I want to do here is I want to find what does it represent. Well, the definite integral, if you remember correctly, is the area under the curve, right? So whenever you see definite integral, you're thinking area. And so the definite integral is going to represent the distance that Izzy runs in 3.75 hours. So the distance that he runs in 3.75 hours. So now in my diagram, I want to draw 5 trapezoids to represent the definite integral, and we'll use the trapezoids to determine the area. So I'm going to do this on Desmos because it's a little bit easier to do that way. I'm doing 5 trapezoids. I'm going to 3.75. So that's going to be somewhere right in here, I guess. Let's see. There's 3.75, so right there. And so what I might do is I might just try to draw this in here. Not the best drawing, but we'll see how it goes. So it looks like this is going to go up to about right here. Oh, I don't know. We'll see. Looks something like that. It's not the best drawing, but we'll see how it goes. I'll make that bulleted so you can sort of see it a little better. All right, and we want to draw 5 trapezoids here. So 5 trapezoids. I want it to end at 3.75. I need to divide this into 5 equal regions. So how do I figure out what my base is going to be? Because remember, I need to have equally spaced trapezoids. Remember that delta x, which is my base, right? That's going to be 3.75 divided by 5. That will tell me how much each one of those needs to be. And then when you do that, you can see that each one's going to be 0.75 wide. So that's easy enough. I can simply just go from 0 to 0.75. There's 1.5. There's 2.25. There's 3. And then there's 3.75. So you can see that all these are sort of equally spaced apart. I can visualize these as being, this being A1. Oh gosh, also have to do all that. This being A2, A3, A4, A5. All right. Hopefully that wasn't too bad. And so now we want to estimate the value of the integral by calculating the area of those 5 trapezoids. All right, so pretty gross. We can do this using actual numbers if you wanted to, or we can do this sort of using estimates. And so I'm going to do this. Oops, scroll too far. I'm going to do this using the actual numbers, and so here's what you get. So A1 is 0.5 times 0.75 times that should give you 4.3125. And what I'm going to do is I'm going to go ahead and skip ahead just so I can give you A2 should be, and once you sort of add all these up, right, all the way to A5, that should give you something in the ballpark of 26.1. Remember, my units here are going to be, let's look again to make sure. Yeah, my units are going to be, what is he running in? Miles, right? Yes, he's running in miles. So my units are going to be miles. So there we go. There's the trapezoidal rule. I am going to skip this last part here. This last part is, I'll go ahead and give you the answer just in case you want to try that. But the answer should be, you have a total of 7,200. The units are cubic feet. Go ahead and see if you can get that one. And then hopefully you can, and we're good to go. I will hopefully talk to you guys soon.